So, yeah, we'll have a time to do a couple problems, but just to remind you some things, because it's been a while, I think. For test 2, you're going to need to know limits in detail. So know how to tell they don't exist, tell they don't exist, and prove when they do. All right, for this prove when they do exist, we had those two things. We can use either the skews theorem, or you can use polar coordinates if applicable. I'm also going to ask you about extrema, which is the topic we've been doing just now, both local and absolute. So know how to find those and classify them and find that. Chain rule. So I'm going to ask you to differentiate a bunch of stuff, write down some formulas for the chain rule, how to use it. Develop formulas. You're also going to need to know directional derivatives.
When you say develop formulas, that means like solve it?
Yeah, like I'll tell you about some random function. I said find partial of w with respect to z, and I put like 5 variables in there. You should be able to write down a formula. Right, this, how to find them. Direction of like max increase or min increase, direction of max or min increase. Of course, tangent planes. And as I said, tangent. I believe, what section was it that we learned about the gradient formula for it? That was 11.6 form. The form you learned earlier doesn't matter. This form captures that. Note this one. That's the guy that says, oh, it's partial of f times x minus x naught plus partial of y times y minus y naught plus partial of z times z minus z naught equals 0. That whole formula about z minus z naught equals little fx x minus y. That one, you can just don't worry about it. Like this one will work in all cases. Just bring everything to one side and find the gradient, and that's going to be your.
Wasn't the formula for the formula where it was like if you wanted to find dz over dx, you put.
Yeah, that will be under chain rule. So implicit differentiation. Yes, you should know that.
Yes, alright.
That falls under chain rule.
I was talking specifically about the one where it's like.
Yeah, so that one's like dz dx is minus partial with respect to x over partial with respect to z. That formula, like you should know it.
That's like the shorter version of the long one, right?
Yeah, that's like implicit differentiation in a single formula. I think that's it. For bonus, I'm going to ask you about integrals. So bonus.
Oh, are you sure?
Iterated into it. Some simple problems. Maybe I'll ask you to evaluate something like that. So in the next section, we're going to talk about integrals in higher dimensions. We're going to do double integrals, triple integrals, that sort of thing. So you might see something like something like that. Do you know how to actually compute that, or how to deal with it, or what it means, how to set it up, etc. So yeah, that's basically what the graph looks like. That's pretty much it. Yeah.
For directional derivatives, because you were saying for tangent planes, is it to find the gradient vector? Isn't the formula for 11.6? Isn't that for
the gradient is used in both of these, but it's not like they're the same thing. Like a directional derivative and a gradient vector are different, right? Remember, this is a scalar. A directional derivative is a scalar. It's a dot product, right? This is also a scalar, but it's the formula for a plane. It's a very specific formula.
Oh, because I thought that formula, it looks kind of familiar to like the linearization that we did for tangent planes and all that. Because tangent planes was 11.4.
Right. The linearization formula, which is sort of that one,
yeah.
It's a special case of this. If you know this, you automatically know that.
Oh, okay.
Right, in this formula, what happens is the partial of z, f with respect to z is actually 1. And then you move it to the other side. So that's what happens there.
So we could, like, if we know that.
If you know this, you automatically know that.
Yeah.
So the linearization will be on it too.
In the case, because in the case where you have something like z equals f of x, y, right? What you would do is you'd move everything to one side. And then if you take the gradient of this, right? The gradient of this would be fx, fy, and minus 1 for the z. Right? And so if you plug that into this formula, you would have fx times x minus x naught plus fy times y minus y naught plus you have minus 1 times z minus z naught equals 0. And then you move this to the other side. And then you get that formula. So this formula has that built in. This is just a special case of that. Yeah.
We also have to then solve for that, by moving x and y.
Yeah, there was that issue. There are times when they give you only 2 coordinates, like they say, find it at the point 2, 3. The thing is the z coordinate. You can't just assume you know what it is. You have to actually use the original formula. You have to plug 2 and 3 back into this to figure out what the third coordinate is, right? So if it's not given, you have to figure out, it has to be consistent with the function here. Right, so if they just tell you x is 2 and y is 3, you have to plug it in here to get what your z naught is. Yes? Yes.
Will the quizzes be posted online?
6 and 7? Yeah. I'll post those this weekend. And tomorrow. Other questions? General questions? I think I tested you on these before.
Yeah, you did.
So yeah, the next quiz would be purely on this stuff, extreme.
That's going to be on Tuesday?
Yeah. Again? Differentials and linearization. Did I put that on it? I think so. I think I put a linearization problem on it. I don't remember exactly what chapter we put that in. But yeah, also know about differentials, linearization.
Differentials and linearization, they were in, I think, 11.4.
I should put one of those on it because they show up on the finals all the time. So yeah, this test is packed with like vital information. Like all of these like show up on pretty much every final. So it's good stuff to know. Any other general questions? Any specific questions from the homework?
Yes. Did you go over
Yeah, the optimization ones won't be on the test.
You said will?
So will not.
Oh, okay.
So Is that an optimization problem?
No, it's trying to find
The absolute.
absolute
Okay.
maximum.
I mean, we could do those, but I'd probably not do it. Do it at our leisure time. This is 23. What was the function?
Fxy equals x squared plus y squared minus 2x. And it's closed on a triangular region. So it's 2, 0, 0, 2, and 0, negative 2.
So I draw that region first. Okay, so I have 2, 0, which is here. I have 0, 2, which is here, and 0, negative 2. So it's so that would be my region D. I can call this D1, D2, D3. D3 is what curve?
X equals 0.
It's x equals 0, and what's the range for y?
The range is
Negative 2 and 2.
Okay, D2 would be what curve? Y equals minus x plus 2, right? And the range for x? 0 to 2. This one?
X minus
Y equals? X minus 2, right? And the range for x? Right. So for all your boundaries, you have to be able to tell this information. What function describes it? So you have y as a function of x, and you'd have to know the range on the x, right? So every time you the variable over here, you have to know the range of that variable. So that's before I even start the problem, I'll get that out of the way. Then I'm going to try to find, what's the next thing?
The partial derivative.
I need to do the partials for the critical points, because I need to make sure, I need to know if there are critical points inside that region. So fx would be 2x minus 2, fy would be 2y. So this means my x must be 1, and my y must be 0. This means 1, 0 is the only critical point. Is 1, 0 in this region?
Yes.
Yes. So 1, 0 is right here, so it's important for me to know the value of the function at this point. So I'm going to find f of 1, 0. I'm going to plug it into this function, and that is what, minus 1?
Yeah.
Right, so that's a value that I need to know. Now I'm going to move on to testing the boundaries. Now test boundaries. So now if I look at D1, and I know what D1 is. D1 is y equals x minus 2, where my x is ranging from 0 to 2. And so now I'm going to create a new function, g of x, which is defined as x comma x minus 2. So I'm going to replace all my y's with x minus 2's. So I'm going to have x squared plus x minus 2 squared minus 2x. Plus 2x squared minus 6x plus 4. And then what I'm going to do is I need to find the absolute max and min of that guy on this interval. So I'm going to find the critical points. 4x minus 6. This means I need x equals what? 3 over 2. It's critical point. So I plug that into the function. 3 over 2 is in this interval, so it's something I have to test. So now I know that g of 3 over 2 is really going to be f of 3 over 2 comma 3 over 2 minus 2 is what? Minus a half. And so now I'm just going to plug in 3 over 2 into this guy, which is going to be nasty. It's going to be 2 times 9 over 4 minus, well, 9. So it'll be 9 over 2 minus 9 plus 4. That's going to be minus 9 over 2 plus 8 over 2. It's minus a half.
Where'd you get the first minus half from the y coordinate? From what you wrote the g of 3 has? Where did you get the minus half from?
Hi, can you guys be quiet over there? Which half? Which half?
The one where you wrote g of 3, which is, yeah, that one.
For my function. My coordinates come from x and x minus 2. So my x is 3 halves, I plug in 3 halves here, I get that. So I know this is one of my points, f of 3 halves comma minus a half, and the value is minus a half there. And now I'm going to do it for D2. And D2 was y equals 2 minus x, where my x ranges from 0 to 2. Oh, I have to test the endpoints. Test endpoints. So my endpoints are going to be g of 0, which is f of 0 comma minus 2, which is going to be, if I plug in g of 0, I just get 4. My other endpoint is going to be g of 2, which is f of 2 comma 0. And I'm going to plug in 2 here. So that's going to be 8 minus 12 plus 4. All right, so that's minus 4 plus 4, let's see. Now I move on to D2. I will do y equals 2 minus x, where x ranges from 0 to 2. So I create a function g of x, which is f of x comma 2 minus x. It turns out it'll actually give me the same function as before. Right, because the y is squared. So this is x squared plus 2 minus x squared minus 2x. This is the same function as before. X minus 2 squared and 2 minus x squared is exactly the same thing. This guy's going to give me the same points. So I'm going to have here, I know 3 over 2 is going to be a critical point. In this case, it's going to be 2 minus 3 over 2, which is going to be 1 over 2. And I'm going to have to test the endpoints, which are going to be at 0. And I'm going to test this point, which is going to be at 2. So I put in 2 here, 2, 0. So here, if I put in 3 over 2 with minus a half for the y, I'll actually get the same value because the y is actually being squared. So this would also give me minus a half. 0 and 2. And 2 and 0. So those are the guys here.
The way to test the endpoints that way, like you do like each one for each like D1, D2, and D3, doesn't it kind of like it overlaps a lot?
Yeah, it'll overlap. One thing you'll always realize when you do enough of these problems, you will always test the extreme points of the curves. Like this will always be a test point, that will always be a test point, that will always be a test point.
Yeah, so
Essentially the endpoints of your line, you test these 3 points.
yeah, so why don't, instead of doing it like this way, why don't you just find the critical points, test those, and then at the end just test the 3 endpoints. So you don't have to test each one twice. Which is like the way that's going to happen now.
Well, what you could do is you can notice that what you're doing here is just going to be a repeats and you look back. One thing I don't want to ignore that is because it's possible that some other point might develop like on this line actually.
Yeah, and that's where you find the critical points, and that's where you can.
Yeah, that's where the critical point is.
Yeah, but the endpoints are always the same.
The endpoints will always be the same. Yes.
So you still want us to test each one twice, or can we just like go to the end and test
No, like for example here,
Yeah, that's
You
already.
write that down. You just know it's really the same guy here.
Okay, but you want us to write it down twice.
If you're setting it out this way, I'd want you to write down twice. If you put, you can put like a section where you just said endpoints,
Yeah.
and you just say, I'm going to do f of 2, 0, I'm going to do f of 0, 2, I'm going to do f of
Negative.
0, negative 2. And then you find that section, and then you can skip this section
Yeah.
for each of the three
Yeah,
parts.
yeah.
That'll also be fine.
Okay.
So yeah, because these guys you're going to actually find them on every line in the endpoint section. So anyway, continue. D3 is the last one. In D3 we just have x equals 0. And our y ranges from -2 to 2. Which means I'm going to create a function f of, it's going to look like f of y, or g of y. Which is f of 0 comma y, which is just y squared. Okay. This means y equals 0 is the critical point. And so from this guy, I'm going to test f of 0, 0, which is 0. And then I can redundantly put in the endpoints, which in this case is going to be 0, 2, and 0, -2, which I would have computed those before. 0, 2 is 4. 0, -2 is also 4. Those are all the boundaries, and now I can finally answer the question. So I should be able to say what my absolute max is at this point, and what my absolute min is. What's the absolute max? 0, 2.
0, 2, 0, -2.
Right. So 0, 2, and 0, -2 gives me 4 is my absolute max. The absolute min? F of 1 comma 0. What I might do on the test is, actually for the extremer problem, I give you like one function to do everything. So I'll ask you to find critical points and classify them, and then I'll ask you for that same function, what if I give you this region, and you have to find the absolute max and min, right? So you'll save some time on computing partial derivatives. You can just reuse the ones from the previous part. But I might do something like that.
What if when they're giving you like the region, like it always gives you like inclusive or inclusive endpoints. If it's non-inclusive, then would you just find the
What do you mean not inclusive?
So if it says like the region is like brackets to
Oh, they can't give you that. That's not, because the theorem that they want to use doesn't apply in that case.
Oh, okay.
It has to be a closed boundary, they call it. Yeah, so they'll always have to give you where the endpoints are included. They'll always be included. The theorem, it just doesn't work there. Because it has to do with continuity and being defined at the edges. The theorem that makes all this work requires that. So you can't do it on an open window.
I was thinking that you would just find like find f(x) and fy partial derivatives, and then just find like whatever the min or max point is there. But
No. Because the problem with that is it's possible for, like, on the boundary, if you don't include that, it's possible for your function to do something crazy like create an asymptote and shoot to infinity.
yeah, okay.
And that messes everything up.
Yeah, you won't be able to find it.
You won't be able to do anything. Right? So they want you to be able to find the function evaluated at the endpoint, and that's like, we can find a definite answer. Like, the theorem wouldn't work otherwise. Because there's a theorem that says we're guaranteed to be able to find an absolute max and min, right? In a case where we like shoot to infinity, there is no absolute max. So we're not, that guarantee is not there anymore, and we're not in the situation. It'll always be a closed boundary. Any other questions?
33.
actually out of time.
Well, I think 31 through 33. That's optimization.
31 through 33, the optimization ones where it asks about finding the minimum this or
It's like they said find the point on the plane the closest to the point. Blah blah
yeah,
blah.
problems like that. Don't worry about them. We can look at those later. I can talk about those on Tuesday, but they won't be on the test. Very unlikely to be on the final, also. So for now, we won't worry about
What do you
it.
want us to put
Leave your homework here.